Okay. Yes. Are you with me?
Yes, we are with you. Go ahead, sir.
Okay. Thank you, Chairman, sir. Good evening, members of this group. My name is Muhammed Yahuza. I'm here to give a review on generating set of completely zero simple semigroups. A paper written by Robert Gray and Roscoe in 2005. So this is the outline of the work. Now, definition: a semigroup S is said to be completely zero simple if it is zero simple and has zero minimal left and right ideal. So by simple semigroup, we mean a semigroup that does not contain proper ideals. So if that semigroup contains zero, then we call it a zero simple semigroup. And if it has zero minimal left and right ideal, then we call it a completely zero simple semigroup. So this work concern only finite semigroup and in particular with finite zero simple semigroup. Every finite simple semigroup is completely zero simple semigroup. So you can see how we 1995 for more on this. Now Rees matrix semigroup. Let G be a group and I and lambda be non-empty finite index set. So by index set here we mean I and lambda, the element of I and lambda are used to label the matrix lambda cross I. So P is a regular lambda by I matrix over G union 0, where G union 0 is the principal factor of S. Then the principal factor of S corresponding to J is the set J star, which is J union 0 with multiplication defined in this way. So here what we are saying, we can have a zero simple semigroup in a natural semigroups. That is, if you just take a J class, then you adjoin 0 to it, then it becomes a zero simple semigroups. Such that if you take the product of two elements, if the product is inside the J class, then you have it there. Otherwise, you have zero. Then the semigroup J star is either a semigroup with zero multiplication or is a zero simple semigroup. So here we'll be making use of the standard notations in semigroup theory, such as the Green's R, L, H, J, and D relations. So we will use R subscript I, comma, L subscript lambda, and H I lambda to denote the R, L, and H classes indexed by I in I, and lambda in lambda, and I comma lambda coming from I cross lambda respectively. We will also use E of S and F of S to denote the idempotent of S and the subsemigroup generated by them respectively. Now here are some facts on the Rees matrix semigroup. Let M into G comma I comma lambda comma P be a Rees matrix semigroup over a group G, then I comma A comma lambda is an idempotent element if and only if the entry in the matrix corresponding to I and lambda is not zero, and the entry corresponding to I lambda is equals to A inverse. Now another thing is this semigroup is a regular semigroup, because if you look at the I comma A comma lambda is R related to J comma B comma mu if and only if I is equals to J. Likewise, this element is R related to the other element if and only if lambda is equals to mu. And these two elements are H related if and only if I is equals to J and lambda equals to mu. That is their intersection. Now the D is equals to the J classes, which means we have just two J classes, 0 and the M0 by 0. So it means we have 0 and M0 as the only ideals of this semigroup. Now the rank of completely zero simple semigroup. The following lemma state the obvious fact that a generating set for this semigroup must intersect every R and every L class of S. So we have a lemma 1, and this is from the work of Ruskok 1994. It said, let S be a completely zero simple semigroup, then the rank of S is greater or equals to the maximum of the size of the I, comma, the cardinality of lambda. Now, as a direct consequence of Green's lemma 1995, it follows that if A generates every element of a single group H class and at least one element in every other H class, then this is enough to say that A generates the whole semigroup S. So more precisely, we have this lemma from Ruskok 1994. It says if S is a semigroup, if S is a completely zero simple semigroup, and H I lambda is a group, and let A be a subset of S. So if H I lambda is a subset of A, and A intersection J mu is not equals to 0 for all J belongs to J coming from I and mu coming from lambda, then S is generated by A. Now, rectangular zero band. A rectangular zero band denoted by S equals to M0 into 1 comma I comma lambda comma P is a zero Rees matrix semigroup over the trivial group. So this means the middle component of every triple equals to 1. We can effectively ignore it and consider the semigroup of the pair S equals to I cross lambda union 0. Because you can see the group here is the trivial group, which consists of just 1 as the only element. So that is why, and from here, if you check back, we'll see that this semigroup is having I cross G cross lambda. So here our G consists of only one element. So therefore, it means every triple element will be equals to 1. So therefore, we can effectively ignore it and consider the semigroup of the pair S equals to I cross lambda union 0, with I ranging from 1 to M and lambda from 1 to N, and P a regular N by M matrix over 0 and 1. And the multiplication is given by, if you have two elements I lambda into J mu, then this is equals to I lambda if the n3 corresponding to lambda and J is equals to 1. Otherwise, we have 0. The same thing, I lambda into 0 will get 0. Now we'll call two n by m matrices A and B over 0 and 1 equivalent. Writing A equivalent to B if B can be obtained from A by permuting its rows and columns. That is, if you can permute the rows of A, and from there you can get the matrix B, then you say A is equivalent to B. That is, permuting rows and columns means just interchanging the rows or columns. Now, clearly, this equivalent relation, this relation is an equivalence relation on the set of n by m matrices over 0 and 1. That is, the entries of this matrix are just between 0 and 1. And a special case of Howe 1995 theorem 3.4.1 says two matrices are equivalent if and only if the rectangular zero band that they correspond to are isomorphic. Now we have a definition here. So let P be an M by M matrix over 0 and 1. We use P into I1, comma, up to IL into J1, comma, up to JK to denote the submatrix of P obtained by deleting all elements with first coordinate in the set I1 to IL, or second coordinate in the set J1 to, sorry, here is supposed to be JK, not KL. We use 0 when no rows or column are to be deleted. For example, P of 0 of 1 means leave the rows alone but delete column 1. I hope this definition is clear. Now, we have a lemma. So this lemma is saying that if you have a non-singular matrix, you can delete a row or a column, and at the same time you maintain the regularity of that matrix. So let P be a regular n by m matrix over 0, 1. Then if m is greater than n, then there exists j in 1 comma up to m, such that q, this q is the sub matrix, that is by deleting the jth column. So q equals to p into 0j is regular. So that is, if you delete the jth column, then this sub matrix will still be regular. Now, number two, if m is less than n, then there exists I in 1 to n such that q equals to p of I of 0 is regular. So likewise here, if m is less than n, then you can delete the ith row in the matrix, and still the submatrix q will be regular. Now here, number three, if n is equals to m, that is the rows and columns are the same, then there exists j into 1 to n such that p of 0j is regular if and only if there exists I in 1 to n such that q equals to p of I of 0 is regular, which is the case if and only if p is not equivalent to in, the n by n identity matrix. So this condition here is very necessary, because if p is equivalent to in, then this condition may not hold. But p not equivalent to in means if you have an identity matrix, you know that identity matrix is just the diagonals that you have one one, all other entries will be zero. So if you delete any column or any row, then that matrix will still be regular. Now the proof. Suppose otherwise, the first one, so that for all j into 1 to m, the matrix P of 0j is not regular, then for each j into 1 to m, there is a row that has 1 in the j position and 0 everywhere else. And this is correct, because for this not to be regular, it means if there is 1 in the j position, because we are deleting the j column, and if we delete the j column, it means all other rows corresponding to that column will have 0 everywhere except 1 in that z column. So that is why here we say suppose otherwise, so that for all this the matrix is not regular. Now there is a row that has 1 in the z position and 0 everywhere else. Now all of these rows are distinct, and there are m of them, which contradict the fact that m is greater than n. Now, two, we use a symmetric argument to that of the first proof. And three, by the same argument as in part one, it follows that if P of 0i is not regular for all I belong to 1 to n, then it means P is equivalent to the identity matrix. Conversely, if P is equivalent to In, it's clear that for any I in this set, P of 0i is not regular. So this issue of P equivalent over 0i is key here. So for you to prove this, P must be equivalent to the identity matrix In. Now the next is a corollary, which says let P be a regular n by n matrix over 0, 1, such that P is not equivalent to the identity matrix. Then there exists I comma j into 1 to n such that p of 0j comma p of I0 and p of ij are all regular. So, and the proof is by the above lemma, we can find ij in this set 1 to n so that p of 0j and p of I0 are regular. And of course, p of ij will be their intersection, which is also going to be regular. Now, the next theorem is let S be an m by n rectangular zero band. Then the rank of S is equals to the maximum of m, comma n. Now, proof. It follows from lemma 1 that rank of S is greater or equals to maximum of m, comma n. So this lemma 1 is the first lemma from the work of Ruskok 1994, where he found the rank of this semigroup to be greater or equal to this. Now we have to show that we can always find a generating set of this size. We must prove u of m, comma n. If S is an m by n rectangular zero band, then S has a generating set with cardinality maximum of m, comma n. First, we consider the case where m is equals to n and use induction on n. So u of 1 comma 1 holds trivially, because if n is equals to m and we have just one row and one column, then the result holds trivially. That is nothing to show. Now suppose u of k comma k holds, and let t be a k plus 1 by k plus 1 rectangular zero band with I equals to lambda equals to 1, 2 up to k plus 1, and the underlying matrix P. Now, if P is equivalent to the identity matrix Ik plus 1, then it is easy to verify that this set 1, comma 2, comma 2, comma 3 up to k plus 1, comma 1, which has size k plus 1, will generate T. And so we are done. Now, uh, if P is not equivalent to this identity matrix, then by corollary 4, we can suppose without loss of generality that the submatrix M equals to P of k plus 1 of 0, comma N equals to P of 0 into k plus 1, and 0 equals to P into k plus 1 into k plus 1 are all regular. So by our lemma 4, if this matrix uh, is not equivalent to the identity, then we can decide to delete a column or delete a row, or at the same time delete a row and column, and the submatrix will still be regular. That is what we mean by this m, n, and n. So here it means we are deleting the k plus 1 row, and this submatrix will still be regular. Here we are deleting the k plus 1 column and leaving the rows, and this submatrix will still be regular. And here, if you delete the k plus 1 column and k plus 1 row, then the submatrix O will still be regular. Now, let Tm, comma Tn, and sorry, here is supposed to be T0, is a typo. T0 be the subrectangular zero band corresponding to these regular matrices. Now, by the inductive hypothesis, we can find a subset of T0 such that size of A is equals to K, and this T0 is generated by A. Now, let B be equals to A union K plus 1, comma K plus 1, because you can see in T0, we have deleted the k plus 1 row and k plus 1 column. So now here we are adding the k plus 1 and the row and column. That is A union k plus 1, comma k plus 1. So let B be a subset of T. Now clearly the size of B will be equal to k plus 1, because here the size of A is equal to K. Now by adding this element, we are going to have k plus 1 to be the size of B. And we also claim that B generates T. Now, indeed, we have B to be equals to A union this, that is, B is being generated by this A union K plus 1 comma K plus 1. And by equality, we have this where this T0 is generated by A. So we can replace this A with our T0 union K plus 1 comma K plus 1. And now we are left to show that this K plus 1 comma K plus 1 such that I is coming from 1 to k is a subset of this generating set. Because if k plus 1 is in the generating set, then it means we have to show that this is also part of the generating set, because it is only when you have element like this you can multiply them to get another element. Because if this I and this I, if the matrix corresponding to I and I is not zero, and since we are taking P to be not equivalent to B, to the identity matrix. Now let J belongs to 1 comma up to K. By the regularity of M and N, we can find V comma L in the set 1 to K, such that P into K plus 1 comma L is equals to P into V into K plus 1 equals to 1. That is, we can have an entry in the matrix corresponding to this K plus 1 row and the L column to be equals to 1, which is also the same thing as the entry corresponding to V row and K plus 1 column. Then it means K plus 1 comma J is the same thing as K plus 1 comma K plus 1 into L comma J, uh, yes, into L comma J. Because if you multiply these two, because this K plus 1 and the L, you can see here, the entry corresponding to K plus 1 and L is the same thing as 1. So remember, we say if you are multiplying these two elements, the entry corresponding to K plus 1 and this must not be equals to 0. That is, it must be equals to 1. So if this is equals to 1, then you have this and this as the element of the generating set. Likewise here, if you have J comma K plus 1, it's going to be the same thing as J comma V into K plus 1 comma K plus 1. Here, the entry corresponding to V and K plus 1 is also 1 here by this. So therefore here we'll be having J into K plus 1, where L comma J and J comma V are coming from the sub rectangular matrix T0. Now we consider the case where T is an m by n rectangular zero band with say n greater than m. Remember in the first instance, we said let m be equals to n. So here we are taking n to be greater than m. Now by repeated application of lemma 4, without loss of generality, we can suppose that this Q to be a sub-rectangular matrix of P into m plus 1, comma m plus 2 up to n into 0 is regular. That is, by deleting these rows, then this sub-rectangular matrix will also be regular. Now let TQ be the sub-rectangular zero band corresponding to Q. That is, after deleting this, then you have a sub-matrix. So let TQ be the sub-rectangular zero band corresponding to this Q. Since Q is an m by m matrix by the previous case, we can find a subset of TQ with size of A to be equals to m. And of course, A will generate TQ. Now let R be equals to 1 comma lambda such that lambda is equals to m plus 1 comma up to n, and B is equals to A union R subset of T. So clearly here the size of B is equals to n. I will also claim that B generates T. Indeed, we have B is equals to being generated by A union R, which is equals to A union R. Now this A this A generate TQ. So we can replace this A with TQ, and so we have TQ union R. And we are left to show that this I comma j such that I is coming from 1 to m and j coming from m plus 1 to n is a subset of B, that is the generating set. So by the regularity of Q, we can find X in this set such that the entry corresponding to X1, that is the X row and 1 column, is equals to 1. And we conclude that I comma j is equals to I comma x into 1 comma g, where ix is coming from tq. And if you can see from here, this multiplication, uh, this x1, that is the the entry corresponding to x and 1, that is x row and 1 column, is 1. So therefore we can effectively write this multiplication as ig, where ix is coming from tq and 1 comma j is coming from r. So thank you for listening.